So our last section in chapter 5 is putting it together, 5.7, which method do I use? There's two sections in here. One is about probability and one is about counting methods. And since we didn't cover the counting methods in 5.5, we're going to skip that part. So this is going to be a really short lecture video. And this is the most important slide in this lecture, which gives you kind of a step diagram about which probability rule to use. So let's walk through this. So the first question you're asking, are you finding the probability of a single event? If so, are the outcomes equally likely? Okay. If they are, then just simply use the classical approach, which is the probability of E, which is the number of outcomes of E over the number of outcomes in the sample space. If the outcomes are not equally likely, the question you ask, is it possible to get empirical data? And if you do have empirical data, this is just the frequency of E in your observation over the number of trials. Okay. And again, notice that here we're talking about approximation, not an actual equal of the probability. If it's possible to get it, if it's not possible to get empirical data, then you need to use subjective probability, where you're making more of an estimate, etc. If we're not talking about a single event, then we're asking ourselves, do the events involve the word or, and, or at least? Okay. If they involve the word or, then we have to decide whether they're mutually exclusive or not, right? That there's nothing in their intersection. If they are mutually exclusive, for example, if we're rolling a die and one's even, one event E is an even number and F is an odd number, we know that they're mutually exclusive because no number, no roll can be even and odd. So if they are mutually exclusive, we simply add the probability of each event. If they're not mutually exclusive, remember this is where we have to subtract out the intersection, what members are in both, so that we don't double count them when we first add the probability of E and the probability of F. We subtract any members that are in the intersection. This stops us from double counting those results and skewing our probability calculation. Going back to whether they involve or, and, or at least, if they involve and, then we have to determine if the events are independent. If they are independent, that selecting one has no impact on the other, then we just use the probability of E and F is equal to the product of their probabilities. If they are not independent, then we use the probability of E and F equals the probability of E times the probability of F given E. Okay? All right. And then finally, if they multiple events include the word at least, we consider using the complement, and then do 1 minus the complement. This says at least 1, but it could be at least anything, and then whatever the complement would be. Okay, so this is a really important table. I suggest you get it in your notes somehow, or just keep reviewing it, knowing what you need to do and when you get to each type of probability. So let's look at an example here. In the game show, Deal or No Deal, a contestant is presented with 26 suitcases that contain amounts ranging from 1 cent to $1 million. The contestant must pick an initial case that is set aside as the game progresses. The amounts are randomly distributed among the suitcases prior to the game, as shown in Table 11 down here on the right. So there are 8 suitcases between 1 cent and $100, 6 between 200 and 1,000, 5 between 5 and 50,000, and 7 between 100,000 and 1 million. Okay, what is the probability that the contestant picks a case worth at least 100,000? So this is a single event, so we must decide among the empirical, classical, or subjective approaches, as we saw in the last kind of chart, to determine the probability. The probability experiment is selecting a suitcase, and each prize amount is randomly assigned to one of the 26 suitcases. So the outcomes are equally likely because they're just picking one suitcase out of 26 and they're randomly assigned the amounts in them. Show the 7 cases. Table 11 shows that 7 cases include at least $100,000. Letting E be worth at least $100,000, we compute the probability of E using the classical approach, which is simply the number of outcomes of E divided by the total number of outcomes, which is 26 if we add these all up together, or if we realize that there's 26 suitcases. So we get a probability of 0.269. So if we had 100 different games, we'd expect about 27 of them to select a suitcase with an amount worth at least 100,000. Okay. Let's look at another example. According to the Harris poll, 14% of adult Americans have one or more tattoos, 50% have pierced ears, and 65 of those with one or more tattoos also have pierced ears. What is the probability that a randomly selected adult has one or more tattoos and pierced ears? Since we're finding the probability of an event involving the word "and," we're going to let T equal one or more tattoos and E equals ears pierced. Then we must find the probability of T and E. We need to determine if the two events, T and E, are independent. Well, the problem statement tells us that the probability of E is 0.05 and the probability of E given T, ears pierced given that someone is tattooed, is 0.65. Because the probability of E does not equal the probability of E given T, the two events are not independent. And so we need to use the general multiplication rule, which says that the probability of E and T is equal to the probability of E times the probability of E given T. And so we put those two factors that are given to us, 0.14 times 0.65, and we get a probability of 0.091. Okay, about 9% of the times this would happen, or about 9% of that population. Okay, so that's the end of chapter 5.7. Like I said, it's a really short lecture. I didn't realize it was going to be so short, or I probably would have combined it with the last one. But that's kind of a nice break.